rate is a function of environmental temperature, obviously in a temperature-regulating animal, reveals to us that in order to stay warm below the thermoneutral range, an animal has to increase its energy expenditure in order to maintain its body temperature. And because this is a resting animal, we know that this increase is not due to the animal doing more work, moving around, exercising. Now, there is ATP used in staying warm when it is a shivering animal. Shivering burns ATP. That wasteful use of ATP generates heat, and that's part of our ability to stay warm. But metabolic thermogenesis does not consume ATP and is a mechanism for generating heat instead of ATP from the larger scale fuels like glucose. Remember that the expenditure of energy to maintain homeostatic temperature is part of a paired negative feedback loop. The hypothalamus detects low temperature and it sends messages for vasoconstriction to occur. But that does not contribute to the energy expenditure. Shivering and metabolic thermogenesis are the ways we spend energy to stay warm. It's a negative feedback loop because that increased body temperature leads to the thermostat shutting off the heating mechanisms. That's why it's a negative feedback loop. Because we know that metabolism itself, the chemical reactions in metabolism, generate heat, it's easy to understand that increasing metabolism will increase heat generation. But remember that this is a resting animal, and so this animal is not spending more ATP. Outside of shivering, let's say we're talking about an animal that doesn't have shivering as part of its toolbox. So a non-shivering animal has to generate heat, but is not consuming more ATP because it's not exercising. And if it's not consuming more ATP, you can see from this diagram that an increase in ATP concentration would lead to inhibition of phosphofructokinase, which would lead to, well, slowing down metabolism. So from this diagram, you might conclude that it is impossible to generate heat in response to low temperatures without doing more work because of this negative feedback loop. Metabolic thermogenesis is a way around that problem. When we talk about metabolism, in this instance, we're talking mostly about catabolism. Catabolism is the process of breaking down biomolecules to extract energy. And so in this case, what we're doing is breaking down glucose to get ATP. You have to remember that glycolysis is part of catabolism, the Krebs cycle, shunt of pyruvate into the mitochondria, the electron transport chain. These are all components that you have to be familiar with. So I know you learned about this in 211. I have to remind you that the purpose of the electron transport chain is to pump protons into the intermembrane space so that when the ATP synthase lets those protons back into the matrix, it can convert some of that kinetic energy into the chemical energy of that bond added to ADP that makes ATP. But if you were to speed up all of metabolism, based on this diagram, you would of necessity be increasing your rate of ATP manufacture. Problematic, since we've already stated that there is no increase in ATP use. The solution? is the existence of something called an uncoupler protein. The uncoupler protein is an alternate path through which protons can exit that intermembrane space. So protons are no longer only going through the ATP synthase, they're also going through the uncoupler protein. To what extent? Well, as soon as the uncoupler protein begins to work, that would, you would think, slow down ATP production because some of the proton motive force is being used for something else. But remember our negative feedback loop. Remember that ATP, when it drops, leads to an increase in the rate of phosphofructokinase. Phosphofructokinase increase, since it's the rate-limiting step in all of these processes, is going to lead to more ATP manufacture. So by maybe instantaneously reducing ATP production, you very quickly restore whatever ATP production is required for the homeostasis of ATP to be maintained. What the uncoupler protein is doing is increasing the rate of all of these processes that come before the electron transport chain, and including the electron transport chain, in order to generate enough proton motive force to make up for that which is being spent by protons leaving through that proton channel.